Thanks for inviting me to speak here, Munza. Really delighted to be here and really pleased and impressed with what you and the others have achieved with IDSS. It's very hard to put together an interdisciplinary group. I know we spoke about IDSS even before it was conceived, but the pulling it together, and yesterday at dinner was very evident that not only you guys are doing interesting work, but actually even enjoy each other's company outside of work, which is not always the case when you have interdisciplinary, social connections are not that easy to make. Okay, so very impressive, and all really goes to you and your own skill as a administrator. So kudos. So what today I was going to talk about, there are two types of network that you see. Financial networks, that is, networks which are involved in financial trading. This literally is just the pipes that link market participants to matching engines. And so they are custom bespoke data centers. And the second is public clouds. How do we move these very stylized financial trading platforms to the public cloud? Because that's not very easy, because the public cloud is very heterogeneous, very it underperforms in many ways. You can think of this as trying to do something like open heart surgery in an ambulance. That's what it would be like if you try to move. Okay, but what can we do to the cloud in a minimal way that'll help move exchanges? That's the topic. Okay, but there's a larger question here: why did the cloud become? Why are public clouds the way they are? And it really has to do with the role of time in distributed systems and networks. Okay, so I'm going to just say some things that are well known, but take a particular point of view. Networking was really early on was all circuit switching until packet switching came. And there's no question that the transition has been enormously successful. We have, internet, data centers, mobile networks, everything just running on this packet switch technology. And similarly, computing had mainframes or monolithic systems until almost simultaneously with packet switching. In fact, on top of packet switching, we went with distributed cluster computing. Okay, and then now this union has resulted in many things, but one notable thing is cloud computing. Okay, and everybody agrees that this transition has been a massive success. In fact, since the mid-90s, this is really what has been the let's say internet economy and series of these things, right? So there's the internet connectivity, and then there's the web, and then there's social networking. This is one after the other. It's been delivering massively, but we've let something go. The thing we let go of was a common clock. So in a circuit switch network, as you know, there's one clock. So my slots of time are dedicated to me, and the slots are understood in every circuit on the path that connects the sender, the two sides of the conversation. Same thing with mainframe systems. They have a single clock. And so you get very deterministic performance in communication networks. You have centralized control and dedicated resources in computing. This was what it was. And we let that go for something that we call best effort service, which means a network with random jitters. You can't even guarantee delivery of a packet. You have lots of retransmissions, lots of timeouts, and everything works. Okay, and in fact, this is actually a very clever trade-off. Someone in the early days of distributed systems and packet switching made not someone, but a community of people just give up on, let's not worry about synchronizing clocks on these different nodes, because that's a nightmare problem on its own. Okay, and in other words, if the network is reliable, it's very easy to communicate time over the network. If the network is unreliable, it's very hard to communicate time over the network. And so the one and the other go together, right? So if you have a good network, clock sync is not difficult. And conversely, if you have clock sync, you could do things even on bad networks, okay, to make them do better. So it's really it's a very interesting, very important trade-off someone made, and it's been helpful. So what is a distributed system? If you look at the Wikipedia definition, and this is basically the general textbook definition, it's a system whose components are located on different network computers which communicate and coordinate their actions by passing messages to achieve a common goal. That's a distributed system, okay? And the three characteristics that distributed systems should have are that the components should perform concurrently, okay? So what is not a distributed system, as an example, if you look at poker, the way it's played, is one player at a time, okay? There's no concurrency in the way game is structured. It's turn-based, okay? Distributed system is not that, so that we get maximum throughput and maximum performance. Everybody has to perform concurrently. And the components are to fail independently, okay? That's natural. The lack of a global clock is not a design requirement. It's just, as I said, very convenient assumption. So let's not worry about clock sync, okay? Now, if you look at what is a distributed system, just about every modern, electronic system or computing system is a distributed system. Just about everything out there. Databases, clusters, blockchains, ledgers, pub subsystems, financial trading systems, multiplayer games, all distributed systems, okay? And what happened very quickly in the early to mid 70s, this sort of assumption that we will not synchronize clocks became a bit more. Achieved this sort of bugaboo status. We began to teach in textbooks that don't synchronize clocks. Okay, just don't assume that clocks are synchronized, but also let's not bother doing it. It's just not easy. And in fact, this is one of the papers that Leslie Lamport wrote for which he was awarded the Turing Award. He's one of the early pioneers in the field. And it is about how to get ordering of events in the absence of physical clocks. So there's something called Lamport clocks that exist. They're a hybrid. It's called hybrid logical clocks. And he proposed it. It's a beautiful paper, actually. It's worth reading it. And practitioners, also reinforce this. It's just it's dogma, okay? And really, the reason for this is it's been a hard problem. Okay, so what do people do then? What is done currently is the precision time protocol is an IEEE standard, widely used, but in small size, limited size deployments typically. And it says if the network is sort of the enemy in terms of helping nodes at the edge achieve clock sync, why don't we co-opt the network into the distributed time using the network? So all the switches that connect a sender to a receiver are either actually going to synchronize themselves. So A synchronizes with switch number 1, switch number 2, hence switch number 3 like this, all the way to B, the receiver. Or they declare exactly what time was spent in each of these switches precisely, okay? That is, they give the duration. That doesn't require a clock to be synchronized. It just needs the crystal to be running at the right frequency, okay? So that's what you get these. It's difficult to scale this. It's fragile. And so our approach was fundamentally different. We actually said, let's forget about the network. This network is just a noise adder for us. If we find a way to filter the noise out, then we can probably not only estimate the offsets required on clocks relative to a reference, but we didn't correct them, okay? And so this allowed us So you'll see some sort of more, why couldn't this have been in the mid-90s, let's say. It's just the amount of signal processing ideas that had gone from paper to code just hadn't happened, okay? Basic stuff like support vector machines and stuff now are at a level of ease of use and packaged that you can just start doing these things, okay? That's more or less the only reason I can think of. So with that, let me just describe the Huygens algorithm. This is the algorithm that we came up with for synchronizing clocks, okay? So first, what makes clock synchronization? Why do clocks need to be synchronized? Why do they go out of synchrony? Okay. So clocks all have different resonant frequencies. So if you go to the Wikipedia and look at crystals, they're all quartz. It's a piezoelectric material that converts electrical energy into mechanical energy. So they're all cut like tuning forks. They're obviously not all cut the same way, so there's some difference. But the thing is that they're very accurate. They're 5 to 10 parts per million off from the spec. Okay, but nevertheless, sometimes they can be, as a large deviation, they can be off by 20 to 30 parts per million from. In other words, clock A relative to clock B could be off by a few microseconds per second. Okay. The other issue is temperature. Temperature significantly affects the resonant frequency of clocks. And also vibration noise, because it's a piezoelectric material, vibration noise affects quartz. Okay? So here are the non-temperature components. There are two clocks, one on the left. Both are controlled, okay? Finely controlled using our algorithm, but let's just look at the one on the left. That clock is controlled to something in the order of few, tens or hundreds of nanoseconds until this point, and this is done by changing its frequency of ticking frequently. And then at this point, the control is stopped. This clock's frequency sort of goes up and down. The offset actually goes up and down with respect to a reference clock in an almost sort of Brownian motion-like way, zero mean drift. Okay, that's what that is. Here is another clock, which when you cease control, it starts drifting relative to the reference monotonically. Okay, so the thing is that this guy is its frequency is just lower than that of the reference clock. So this is just the heterogeneity of clocks. Here's the temperature effect. So the building in which some of these machines that generate this data are has AC that comes on at 3 a.m. and goes off at 8 p.m. every day. You can see here 2 days. And this is the frequency applied to keep this clock at close to reference, to within a few tens of nanoseconds. Okay, so what you see here is just a very periodic signal reflecting, days, heating, cooling cycles, and how the AC factors into this. It's pretty sensitive. Okay. Now on this side, if you zoom in between 6 and 9 a.m., you actually see the 15-minute power cycle of the AC itself. It'll cool the room down and then shut off, and then the room will warm up. That's basically all you're seeing. Okay, so it's pretty intense, right? That is, it's very sensitive to just mild changes in temperature. So with those two things in mind, right, you have to think of it as you have to continuously keep correcting clocks if you want very fine-grained tweaking. So the dashboard clocks, they're drifting. You live in a hot place, or in the winters it's a certain amount of speed loss, and in the summers it's different, right? So you can see it. I'm sure you all had to reset it now and again. This is, you're now down in the nanoseconds, so you have to do something much more frequent. Okay, so one way you can think of this, because if you're not used to thinking of frequency correction and stuff, it's a very easy way of thinking about it. Think of there being the N clocks. That's the problem. You want to they're connected by a packet switch network, and you want to synchronize them to a reference clock, and one of them is the reference. Okay, so before I give the method out, let me just give you the problem in a somewhat more conventional sense. Think of it, there are n cars in an n-lane highway, so they don't get into each other's way. One of them is the reference clock, and it goes at a certain speed. All cars are going just in one direction on the highway, or the reference clock is going at a certain speed. The problem is to get all the other cars to be exactly the same position as the reference clock. That is, here space and time are made equal. So location in space equals time. Okay, they have to be exactly. Now, what will you do if you're a driver sitting in one of these other cars? You're going to see where this other guy is every so often. If he's ahead, he'll speed up a little. If he's behind, he'll slow down a bit. Okay. Now, if you now make an algorithm out of this, the thing you don't want is everybody checking where the reference is, meaning everybody probing the reference for what's your position is equivalent to what is the time. Okay. That'll just overwhelm the reference. And common mode of failures exist in those sort of systems. It's not robust. Okay. So instead, what we did was say, you can mutually synchronize. So you don't have to. Everybody doesn't have to look at the reference car. You can just look at your neighbors. And at some point, this graph where you're looking at neighbors just has to include the reference. It has to be connected. So then it'll sort of, the position will sort of get aligned through, a few hops. Okay, so that's what this is. So specifically, algorithmically, so that each node picks, let's say, a random number of other nodes. In this case, 5, and they will probe. What that means is they'll send timestamps. Okay, and these timestamps are sent, both directions. So let's get a little bit more detailed. Clock A on the left, clock B on the right. They both have an unknown discrepancy with respect to what's called a wall clock or a reference clock. And the way they want to work out the mutual offset is one guy sends a probe that's acknowledged, and so you get a transmit. Sorry. Okay, so you get a transmit timestamp and a receive timestamp, and vice versa, right? So you have these quadruples of timestamps, and every clock sync algorithm starts this way. Okay, there's nothing else to do but to say the time taken to go from A to B equals the receive time equals the actual transmit time. The actual receive time equals the actual transmit time plus delay. What's going on with this guy? Gather windows. Give me a second, see if I can fix that. Okay, hopefully it'll not come back. So the time, this is the corrected receive time and the corrected transmit time, right? Equals some propagation plus queuing delays. And if you put the unknowns on one side and get rid of that positive quantity called delay, you get a bound on the discrepancy between the two clocks. This is using probes in one direction. If you use probes in the other direction, you will get a bound, and there was a lower bound. Okay. So this is basically what they look like when you plot. This is on Google's 40 gigabit per second testbed, 2 clocks. If you plot the lower and upper bound points, this is what you'll see. You'll see something like this. And what this says is, I'll just read out the salient points here, right? This is time measured according to clock A on the x-axis, 2 seconds of time. The discrepancy is on the y-axis. So the way to read it is that when clock A is at 0 seconds, clock B is 0 minus 93.3 seconds. If you can find the middle red line, I'll come to that in a second. Okay. And similarly, at time 2, clock B is 2 minus 96.6 microseconds. And so it's drifting, it's ticking slower by that amount. And the thick blue line is all the probes that went in the forwards direction from A to B with the smallest possible delay. They didn't get queued, okay, and they went the fastest possible. And the other ones, the thick green line is the other side, the guys from B to A. Now, the middle red line is assuming the A to B and B to A paths are equal in length. If you can find that, separating line or hyperplane, then that quantity will tell you the offset. Are you okay with this? It's simple, basic, right? Okay, so if you look at pairs of clocks at different levels of hierarchy separating them, so they're either in the same rack or in adjacent racks, and there's an intermediate third switch, or further away, and they have 5 hops to go through, you'll see these sort of blue dot, green dot sort of pictures. And so here, the clocks, on the first diagram, the clock, the B is ticking faster, and this is the round trip time, this distance is round trip time, right? This red segment is round trip time. The round trip time is getting bigger and bigger because these two clocks are not further apart and then even further apart, right? But such is the nature of this thing. You can just figure it out, okay? Okay, so now let's assume, I'm going to talk about how to find this middle red line, but let's assume we found it. Then if you plot, this is the relative frequency difference between the pairs of clocks. If you plot the slopes of all these lines, then you expect them to be 5 to 10 microseconds per second apart, because that's what I said is the resonant frequency discrepancy. But of course, once in a while, you can have something really off, ticking really fast, okay? So get this sense that there's a bunch of clocks. We have to keep them synchronized. Temperature is going to be a problem. Wonky fans and servers, which, think of eccentric fans or something, and it starts vibrating. That's going to be a problem. Okay, if the server pumps out a lot of packets, it's going to get hot. Hot servers, so if the server does more work, it's going to have a bad clock. Okay, there's lots of things that you have to just keep on constantly fighting. Are you okay with this? Okay, but luckily, temperature is a physical process. So this is what happens if you look at a 1 minute interval between two clocks. It's no longer piecewise. It's piecewise continuous. It's continuous but piecewise linear, right? So there's no constant slope here. So you have to synchronize at a frequent enough interval, like 2 or 4 seconds. Otherwise, you have this sort of nonlinear clock drifts, okay? Everybody okay with this? So if you can, you should try and do it 1 second or half a second, but then you're just panting with all the work you're doing. That's just not necessary, okay? So let's go find the 3 steps to find this middle red line. And so first of all, you have points of one color and points of another color. You want to classify, use support vector machine. And I'm going to tell you 2 other ideas that we used, okay? So here are support vector machines. So the thick blue and green line, the data points here, how can there be a blue point here? Isn't this least upper bound? Isn't this the greatest lower bound? The answer is yes. It happens that this particular NIC, the network interface card, at which this timestamp was taken, had sometimes faultily recording the time as slightly after the packet was transmitted. Okay, it's just a glitch. So you therefore have artificially smaller times in one or the other direction manifesting as these spurious points in the middle. Okay. Now, if you use soft margin support vector machines, because of the points in the middle, okay, you have got a candidate red line, middle red line. Clearly, it doesn't quite fit because the noise is throwing it off, but still already you can synchronize to a few hundreds of nanoseconds. Okay. Now, how can we get rid of these noisy guys in the middle? Here's another idea, which is it's sort of a differential principle. So think of sending 2 packets. A probe consists of 2 packets. Send them back to back. And for example, the separation of the sender is 10 microseconds. It could have been 6.7 microseconds. You're just trying to send them closely spaced. And then 3 things can happen. First is that when they were received, they got separated by a lot. Should that happen, then you can safely deduce that the second packet must have been delayed more. Whether or not the first packet got delayed, the second one has definitely got delayed, right? That's how it fell behind. We'll reject all those probes. The opposite is possible, in which case we reject all those probes. The third variety is where they're almost separated the same amount, and then it's very unlikely they got the same amount of queuing time in the network. It's very hard for a network to arrange to give 2 packets the same exact delay. Or certainly none of the time noise seems to have occurred. We'll keep those guys, okay? Everybody okay with this? Just taking the bad data points out. If you apply that filter to this picture from before, you'll get rid of most of the, it's not impossible that 2 guys sneak in, but 90% of the bad stuff's all gone, okay? And 90% of the good stuff is retained, which is what you want, okay? So it's somewhat automatic, you don't have to do post-processing. And it'll also work when things are moving, when you don't know what the minimum separation is. So when vehicles are moving, for example. And if you zoom into these things, you always see pairs. There are always pairs at these points, just sneaking in through the network, just coincidentally getting exactly the same delays. So this will improve by a factor of 4. And the final idea is that when you synchronize clocks, synchronization is not just a reflexive and symmetric property. Obviously, it's transitive. So if you look at 3 clocks, you can detect errors. So let's say there are 2 clocks, A and B, and they exchanged probes and done everything so far, and they worked out what is the mutual offset between them. Then the third guy, C. And so if A and B have agreed that if A is at 10, B should be at 10:15. That's the slope offset, they worked it out, okay? And B says, C and B have exchanged probes and they do the same thing. And then C and A also mutually agree, because they've been exchanging probes, that their offset is over here, okay? If C is at 10:05, A must be at 9:50, they mutually agree. Clearly, going around the loop, you've detected there's an error. Okay, it's very easy for any synchronization algorithm could simply have used this. This is an idea that Elon Gang had. And how would you split that excess, the loop surplus of 10 units? There are many ways of doing it, because it's not difficult to see that you'll always have an underdetermined system of equations here. There'll be many solutions. Okay, so now imagine, because we have each node is probing 5 other nodes, there are lots of loops. Okay. And you get lots of loop equations. And now you're trying to work out from a bunch of equations the solutions to the edge offsets, the corrections that must be applied. It's not difficult. It's a simple, nice exercise in combinatorics that the system of equations is always going to be underdetermined. And so therefore, you're looking for, there'll be multiple solutions. And you'll look for and find the maximum likelihood solution. That's what we did, okay? And I'm skipping details here, okay? And if you look at what is the right number of nodes to probe, because K equals the number of nodes a node is probing. Clearly, the more you probe, the more loops you get, the more errors are discovered and corrections can be applied. With a certain diminishing quality to this. Plus, you're just picking up more and more work as you probe more and more, right? So typically 5 or 6, then the mean error doesn't improve too much in most networks that we've seen. But what's interesting is the 90th percentile. It's very hard. It drops down much more rapidly. This improves, but this one's dramatic, okay? It's very hard to be an outlier when you're being compared against so many other clocks. It's hard to be an outlier, okay? So there's, of course, you can adapt the degrees of the nodes depending on your detection of how good or bad they are and the propensity to do more work, etc. So there's adaptive things you can do here. And the step this is all about just inferring. So this is actual stochastic control problem here, right? So this is like the Kalman filter side. So you can figure out the corrections to apply. Then there's the control part, because now each clock has a offset and a frequency, or it's a two-state, system. So it's speed and velocity. And now in the vehicle example, and you want to go correct that, right? And so every 2 seconds, you're going around this loop, find out the errors, and then go back and correct, and keep doing that. And not all the clocks respond the same way. You can, when you're given a set of clocks, in the Kalman filtering and stochastic control sense, you don't know the A matrix. So you have to learn that on the fly. Mostly, you learn it quickly, but different network interface cards we found have absolutely different gains. It's just absolutely different, okay? And the same thing, it ages over time, and its characteristics change. So it's a very interesting, so I'm actually happy to be here with guys like you in the audience talking about stochastic. The systems version of this talk, none of that would come out, okay? So, and you can also actually work out, because now you have a Riccati equation, and you can work out the error propagation along with the estimate, the error, the variance, using which you can, come up with an equation that says by how much are you gaining with the degree k, okay? So let me stop with that. Any questions on this? This is just the one algorithm. I'm going to get into some detail. Yes?
So what accuracy is needed? Up to what detail? How far do you have to obsess over? Is 30 nanoseconds bad? Is 10 nanoseconds? Obviously you want 0.
Right.
You're going to get 0, above 0 Kelvin. So the question is, what is good?
So it comes down to the event frequency in the system that you're trying to deploy these clocks. If your events are happening at the millisecond level, probably microseconds or tens of microseconds is good enough. Because, and if you're in the high frequency trading, this world, high frequency trading world, event frequencies are now down into the few tens of microseconds. So to give you an example, we had a guest lecture from this guy from Deutsche Börse last year, and they talked about how a Cisco switch had one port being 8 nanoseconds faster or slower than the others, okay? And they detected it. Market participants also, they found out of this problem. They had to rectify it. It was just that port should never be used. It was really interesting because now 8 nanoseconds. So let me get to this point a little bit, actually, in the 1 or 2 slides. So if you can synchronize clocks, you can build fair financial exchanges and accurate timestamping of market data, because it's all about how recently was this price at this value. And if you want to synchronize clocks across trading venues, that's the other reason people do it. I'm trading in London. I see this piece of market data from Singapore relative to the clock in London. How long ago was that information taken? So this is now used. There's a startup that came out of this, is used now fairly widely in financial industry, trading firms, and exchanges alike. The point I want to get back to is this cloud, okay? Financial exchanges want to move to the cloud. There's an interesting op-ed in Fortune by the CIO of NASDAQ, and there are others that have been written. What is the advantage of moving to the cloud? You get a bigger size set of market participants. It's very expensive to do, to rent facilities in a colo trading area. What are they doing now? They're in places like this. And it costs a lot of money to get a cage. It costs a lot of money to have an employee or two in a city like Hong Kong or Singapore, wherever they have trading interests. There are 77 venues on earth that people like to trade, 75 to 80 in that order, okay? Actively trade. So, and if they're going across asset classes, like, equities and foreign exchange and now increasingly crypto, this just increases the number of venues you will be at. Crypto is, of course, wonderfully born in the cloud. It's cloud native. There is no on-prem for crypto, okay? So this is where they run. And the most, as you know, just the purpose of any exchange where buyers and sellers meet is to discover price. And this thing runs on top of, when it's electronic trading, something called the trading platform. The trading platform is something that, I'm going to talk about that, but there's a paper which has more details. The market participants, the buyers and sellers, are on the left over there, okay? And each one of those stack of three is the cage belonging to each market participant. And each of them is connected to the matching engine inside the exchange through one or more gateways that the exchange has. You pay for connection through this gateway. If you're not rich enough, you connect to, you share a gateway. If you're rich, sometimes you get more than one gateway, right? So all of that is possible. And then you start trading, okay? And the three components are what I've shown here. I'm saying this is the market participant side. So the gateway through going from the gateway. So market data comes out here, and trade decisions are made, and orders are placed. So this is called tick to trade. That loop is called tick to trade. And over here is the exchange side of the loop. So then here the order goes in, gets queued or executed, results in a trade, and that's the other direction, okay? Now, to answer Ali's question of what's good enough, this time is in the order of 12 to 16, 20 micro, in that order. It depends on the exchange, okay? This loop started at about 2 or 3 microseconds, because if you think of what it is, an Ethernet switch has to look up a packet address. That takes some time, okay? So through a series of innovations, this so-called high-frequency, the speed merchants, they've gone to layer 1 switching. Layer 1 is no lookup of address. Okay, it's a pure demultiplexer and a multiplexer. Wire comes, gets demultiplexed, or array of servers, order decisions are made and flipped around. They even do clever things like, there's an FPGA doing all this stuff now. The market data is coming in. There's a parser reading it. In anticipation of what I'm going to see there, I'm already firing out a response. I haven't seen it yet, but I'm already firing out a response. Bit by bit, this is coming in, bit by bit, this is going out, okay? Now, if it is not the hoped for news in terms of price inside the market data that's coming in, I will corrupt the TCP checksum. Luckily, TCP checksum is the end of the packet. Okay, so my decision that I was already mailing said cancel, okay? And so there's a lot of these bad packets floating around, but they can't wait. It's like these lions eating the zebra before they're dead or something. Like, just let's go, okay? And it's super exciting, actually, when you listen to these guys talk about just the little bit of an advantage. 8 nanoseconds begins to matter here, because now the tick-to-trade time is about 36 nanoseconds. Okay? So the exchange loop must be fair in the most simple terms. If you submit an order that goes through gateway 1 ahead of me submitting an order that goes through gateway N, then at the matching engine, your order should get executed earlier than mine, okay? So you shouldn't be disadvantaged. And when market data is released, all of us should get it simultaneously. So wire length differences are not tolerable, are not tolerated, okay? So it must be fair. So, yeah. Yeah, how would you know? Good question. I see, you're already thinking like a trader. So this is where the multiple gateways come in. Okay, so if Goldman Sachs, guys like that are rich enough, I have gateway 1, I have gateway 2. And I'm placing the same order, I'm saying, guys, look, to the exchange. This is, this discrepancy, okay? There's an audit in the sense that exchanges like to publish how fair they are annually, and it's a point of boasting for them. I'm fast and I'm fair, okay? So come trade with me, because a certain sum of money, you can trade this in Deutsche Börse or Chicago Mercantile, or somewhere else. Well, come to me, okay? So this is sort of this, the exchanges are motivated, just like airlines fighting for common passengers across routes that are common. Similarly, okay? Yes.
So your nanoseconds are inside the. If the party is far away.
Correct. This is a colo facility, yes, correct. If someone is not co-located, then obviously speed of light itself will stop them from, right. Okay, so It's amazing what they do. It's just, I mean, I haven't even exhausted a set of tricks they play, okay? So fairness, just to make it pictorial, yellow crosses ahead of red, but gets to the matching engine second. That's unfair. Whereas if you could, how would you use clocks? A simple way of explaining this is synchronize the clocks down to this level of accuracy that is desired. And then timestamp these orders as they cross the gateway. And then use the timestamp, which now establishes the order of arrival at the gateway, to resequence and exit, at the matching engine. This is actually how, we're working with the exchanges. Okay, so I know I'm being shown the 1 minute signal. Let me just take 1 more minute. Okay, in a talk on timeliness, I hate to be late. Okay, but okay, but and you guys are luckily not a time-sensitive audience. I have demos and stuff if people want to see it later. The thing is not about the fact that you can just solve one problem with many accurate clocks, because I said you can do many things in networking and computing. Sorry, this is just a larger deck. Let me get to this part. I've talked about how clocks can be synchronized, how that could be used to do this. But there's a whole host of problems in networking and distributed systems you can solve more easily, or, as happens in this case, find a new application altogether, okay? And it trivializes some of the problems that exist when clocks are not synchronized well enough. Having synchronized clocks makes it just absolutely easy, okay? It's a huge advantage. So multiplayer games, there's a whole bunch of ways in which people can start using this. Let me stop with that. So just to leave you with the thought, right? Time heals all wounds, right? Timeliness is next to godliness. I mean, there's a lot of things like this.
Right. 1 second.
The first one is there's a lot of movement towards what's called deterministic networking and TSN and all that stuff, time-sensitive networks. Any of that relate to this?
Yeah. This is exactly what it is.
Okay.
The question is, how are you making the network time sensitive?
All right.
We found a way of doing it without taking the network's help.
Okay.
So that's why it's deployable in the cloud. Otherwise, the cloud operator has to make, the conventional layer would be I think the difference here, by the way, is in one sense, is self-driving cars versus self-driving roads. You remember the PATH project Praveen was working on? The highway was supposed to be intelligent. This is the other way, okay? So that was really the dichotomy.
And the other question is, we all have read about the scandals in Wall Street about difference in times between a common trader and the giants. So how do you detect and you police that?
Yeah, so if you're playing the high-frequency trading game, then you are in a colo facility, you are doing all this work. Or you're just doing, you're still doing algorithmic trading, like Citadel does a lot of this algorithmic trading, but it's not high frequency, okay? And it's possible with all the data that's available now and the ability to process it, that's going to tilt, what we've always known as the quant jocks that, companies used to hire from places like Lids and stuff into Wall Street, right? Some of the bots are probably going to take that up, right? It's,
there are a bunch of companies that in Princeton, right, with colleagues that they are the same medical area we are. That's what they do, right? So how do you detect that they take advantage of time?
So in some cases you can, in some cases you can't, okay? If it's systematic and is done something you're losing consistently over time, you can probably tell, right?
That's too late.
It's too late, yeah. No, even with the bot sort of thing, there's the Knight Capital Management is a firm that when you start doing this very high frequency trading automatically, they lost something like $500 million in about 40 odd minutes, and the firm just got shut down. And so people looking for this like sort of stop loss, the handbrake, right, without the hand, right? Something needs to break automatically, right?
Thank you.
I mean, I hate to ask you this question and put you in the spot because you're talking about an algorithm and how it's used on Wall Street, but I'd love to get your opinion. What's the societal benefit of high-speed trading? I mean, it's it clearly only benefits the people that have that edge. It doesn't really, I mean, I've heard the arguments it provides liquidity, but that's a pretty weak argument.
That's the only argument so far, by the way, and the fact that it can be done, and there's no legal reason to not do it. There's an argument advanced in support of the other thing. Can we change the rules of the matching such that it favors just Eric Budish from the Chicago Booth Business School has a proposal for something in the order of once in 100 milliseconds execute trades. Okay, so you have the continuous price time matching, the time component is taken out. Okay, that will discover price, which is what you want, but without having this arms race going on. But I think in some sense, the more I've seen this, the more I felt like the genie is just out of the bottle here. That's what I can. And the cloud may actually equalize some of this stuff, by the way.
Hi. Very nice talk. In your car example, right, where you had N and there was one baseline, and you said you're probing 5 other cars, then would the accuracy also depend on the number of hops it takes to get to the reference car, right? And
right.
Is there some understanding of what that?
Good. Yeah, there is an understanding. Actually, the so-called network effect, which is basically these loops and stuff, it is just, as you saw, it is just purely cumulative. With given n nodes, the more you probe, the more cumulative it is. But of course, the more you probe, the shorter the number of hops becomes, because the choice of paths increases. Okay, so it's less that; it's more about detecting the errors. It's less about the number of hops; it's more about detecting the errors. And there's a bit more understanding on that. The number of hops does matter. So if you have nodes that are genuinely far away from the reference clock, they tend to get affected more. You can change this probe graph. Basically it's a random regular graph, right? In the outbound degree sense. So you can try and make it a purely random regular graph, where then every node is about the same distance from the reference. Yeah, that's.
Okay, Rick.
So seems like there's trade-offs here in how you send the probe, right? And the accuracy you can achieve, and then what the cloud provider is willing to work with in terms of maybe, varying their network to help attract this business, right? Can you talk about that, whether or not some of this could be done at L2 versus L3, and there's quality of service, and like you said, these modern chips can do a lot of amazing things. There's encapsulation. There's all sorts of trade-offs here, right?
Yeah. So I mean, if you want to go for scale, there's a nice question to ask, right? Given the matching engine, at a certain distance in time from this matching engine, how many nodes can we put? Can we have, at 100 nanoseconds away, can we have more than 2 nodes, okay? And like this, you can ask this question. And the more nodes you want to have talking to the matching engine, the further and further away you have to go, just because you have to increase hops. And when you start increasing hops, you leave the world of layer 1 switching, because now in the reverse direction, it's not just a multiplex, demultiplex anymore, okay? So that, usually also, the volume of trading is such that, and the number of symbols listed is such that they shard the matching engine. So you go from A to G over here, and H to something over here, symbols-wise. Okay. So in that world, you don't have the ability to do layer 1 switching. Okay. But nothing. It really is a question of it's what do you want to provide to your market participants? What are they demanding? And how many people do you want to fit? It's really that which nothing fundamentally prevents us from designing networks, except the one I just said, which is at this distance in time from the matching engine. There's almost like a fundamental limit on how many nodes can be actually there that you can support.
Yeah, I wasn't thinking about layer 1, more layer 2 versus layer 3, and how to use these chips and these modern switches.
So many of these guys now do in-band network telemetry, programmable data planes, all this stuff. That's definitely going to increase the speed. They have match action tables that they're already fast. And so that is layer agnostic. It's both layer 2 and layer 3. They do these things. In addition, a lot of the market participants bring their own custom hardware. Intel comes to these kind of conferences where I've seen in the financial world where they talk about how they solve PDEs in FPGAs, and they're very proud of that whole thing. And so in addition to just responding to the trick-to-trade loop, the algorithm that sets the decision, so there's a trading strategy which translates into a trading algorithm. This slower time scale is faster time scale, okay? And this is they're now trying to do this large scale crunching in FPGA, okay? So I think, it'll keep on going this way. I just don't see how it's just technology, is going to, if they'll move maybe from here to crunching large amounts of data, potentially, right? With reading earnings reports, just the usual stuff, using chatbots or ChatGPT type things.